imagine we have a set of n different objects, and we are going to divide these n different objects into r distinct groups of respective sizes. So imagine we have r boxes, we have n objects. We are going to put n1 of these objects into the first box, and 2 of these objects into the second box, so on and so forth, like that. nr objects is going to be put into the art box. So here, n1 plus n2 plus blah, blah, blah plus nr must be equal to n, because all of the objects are going to be allocated. They are going to be put in the boxes. So we are basically creating groups here. The question is this: in how many different ways we can create these groups? Actually, the multinomial coefficients can give answer to that, but this is a generalization of the question related to number of combinations. Okay, so we are going to use the number of combinations and the generalized principle of counting, and we are going to combine this knowledge to find an answer to the multinomial coefficients problem. So imagine this: we have n objects. The first experiment is to create the first group, and in order to create the first group, we have n choose n1 possible combinations. So in n choose n1 different ways, we can select the first group. After selecting the first group, there remains n minus n1 elements in the parent population. And in the remaining parent population, we need to select n2 of them to create our second group. Therefore, n minus n1 choose n2 different ways can be created to select the second group. Once the first and the second group are created, in the parent population, there remains n minus n1 minus n2 members. And from these members, we need to choose n3 of them to create the third group, so on and so forth. Finally, once all of the groups except the last one are created, for the last group, automatically there will remain nr objects, and automatically we need to select all of these nr objects as the final group. Okay, so by the generalized principle of counting, we need to multiply these number of combinations that we create in each selection with each other, and this is going to give us the multinomial coefficients, the number of possible groupings we can create if we have more than 2 groups. So for the first combination, we have n factorial divided by n1 factorial times n minus n1 factorial. If you expand the second combination formulation, you are going to get this. For the third combination formulation, you are going to get this. And for the final combination formulation, you are going to get this. Now, as you can see, the n minus n1 factorial here and the n minus n1 factorial in the numerator in the second component can cancel out. Similarly, the component here in the denominator of the second component and the numerator in the third component can cancel out. Just like that, once everything is canceled out, you will see that this formulation will be reduced to that n factorial divided by n1 factorial times n2 factorial times n3 factorial, so on and so forth, until nr factorial. This formulation looks like the number of permutations of indistinguishable objects, but they are not related to each other. This is called multinomial coefficient, and it is going to answer questions that I'm going to show you in a few slides. Okay, so we denote the multinomial coefficients. The multinomial coefficient is expressed as n choose n1, n2, n3, blah, 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 nr. So we are trying to create a multiple grouping of these n objects into these number of members in each group. Actually, in the binomial coefficient, we are doing the same. So in the binomial coefficient, we write n choose k. However, we do not write n choose k and n minus k. I mean, when you are choosing k elements from n element set, you are basically splitting it into 2 groups, the chosen group and the unchosen group. So in the binomial coefficient, we are doing the same thing as in the multinomial coefficient, just like that. But in the multinomial coefficient, we have more than 2 groups. And this is the formulation for the multinomial coefficient. In the binomial coefficient, you only see 2 factorial calculations in the denominator. Now, in this part, we say a police department in a small city consists of 10 officers, if the department policy is to have 5 of the officers patrolling the streets while 2 of the officers working full-time at the station and 3 of the officers on reserve at the station, how many different divisions of the 10 officers into 3 groups are possible? There are 10 officers. We are going to select 5 of them to patrol the streets, 2 of them to work full-time at the station, and 3 of them are going to remain as the reserve. So in how many different ways we can assign these tasks to these officers? So we are going to create 3 groupings. Each group is going to have a respective number of members of 5, 3, and 2. So this is going to be calculated with a multinomial coefficient. So we say 10 choose 5, 3, and 2. And 10 factorial should be divided with 5 factorial, 3 factorial, and 2 factorial. And this calculation is going to give you a 2,520. For the final question, we have a classroom of 20 students, and we are going to divide these 20 students into 4 equal-sized project groups. So we are going to split these 20 students into 4 groups. In each group, there will be 5 members. How many different divisions are possible? So again, we are going to answer this question with a multinomial coefficient, just like in the police officer's case. We have 20 members. The first group has 5 members. The second group is going to have 5 members, so on and so forth. 20 factorial is going to be divided by 4 different 5 factorials here, or in other words, 5 factorial to the power 4. And the result is going to be a very, very huge number. So it's approximately equal to 12 billion.